And here we go, higher order derivatives. So second last note of this particular unit. This is just more of what we've been doing so that you know that taking the derivative is not something that stops. You can have a first derivative, you can have a second derivative, which means taking the derivative of the derivative. And you can keep going into the nth derivative, meaning you can keep going forever. As somebody who has a math degree, I've only ever done, I think, the third derivative. Sometimes you do more to pick up patterns, but not for actual math. So what we've been doing for the first derivative is finding the slope of the tangent, and we've been using that to find equations of lines, tangent lines specifically, and normal lines specifically. So the second derivative is usually used for a test, as is the third derivative, but do know that there can be lots of derivatives. So the first thing I'm going to go over is the notation, the way you write that you're taking more derivatives. So as you know, there are these three first derivative notations. There's f prime at x, there's y prime, there's dy by dx, and there's also this one, which I rarely use because I can never remember the position of the letters. So it's a capital D and a capital Y kind of on ground level, so the blue line on your page, and then this little x is a subscript. When you move to doing the second derivative, or taking the second derivative, you have a similar way of writing that, only with a squared symbol to say you're doing it twice. F double prime is this one, Y double prime is this one, so it's 2 ticks for each of those. And then I rarely use this one because I can never remember where the little 2's go, but it is d2y by dx squared, or I can never remember even how to say it because I just recognize it as a second derivative from textbook language. Once you get past the second derivative, you can either put on numerous ticks, or as long as you use a bracket around a number, you can say that you're taking that many derivatives. So if you saw, for example, dig out my little tablet, if you saw this means y cubed. That's not what we mean. We mean the third derivative of y. You could also do this, but that doesn't really help you when you get up into like the 30s, for instance, in which case you would want to write it like that to differentiate it, to make sure that you can tell the difference between this and an exponent of 37. So let's tackle a couple of questions. So the first question is find the first, second, and third derivatives of that f at x. So this is a air quote easy question because there's no product rule or quotient rule or power of a function rule. It is simply taking the derivative. So we're going to take the derivative and say we're going to take the first derivative and then do it. So drop the 4 onto the 5 and multiply, make the exponent 1 less. Drop the 3 onto the 3 and multiply, make the exponent 1 less. Drop the 2 onto the 7 and multiply, make the exponent 1 less. Drop the 1 on top of the 9, negative 9, and make it 1 less, which means there aren't any, and the derivative of a constant is 0. So we're done the first derivative. Second derivative, just do it again. So f double prime, drop the 3 onto the 20, that's 60, make the exponent 1 less. Drop the 2 onto the 9, that's 18x to the 1. Drop the invisible 1 onto the 14. Make it no x's, and the derivative of negative 9 is 0. And then the last one, because it's asking for first, second, and third derivative, you can either put that 3 in brackets, or you can put 3 ticks, which I don't believe is that excessive. And then do the same thing. So 60, drop the 2 onto it as 120, make it 1 less. Take the 1 that's on this x and drop it onto the 18, multiply, make it 1 less. The derivative of any constant is 0. So you're done this question. for no reason other than to practice derivatives over and over again. Don't worry, you'll get a reason. So the last question might look like it's kind of easy, but it's not as easy as we really want it to be. I've also changed what the question is asking. So this question isn't asking for the second derivative. Even though it's got the double tick here, this is not asking for the second derivative. It's asking you to take the second derivative and plug in -2 for all the x's. So first step is taking the derivative, the first one, which is going to need the power of a function. So drop the 5, keep writing the bracket, make the exponent 1 less, in a bracket behind, take the derivative of 3x squared minus 1, which is drop the 2 onto the 3 is 6, x to the 1 minus 0. And because we have another derivative coming, make sure that you do, in fact, multiply your monomials together. It'll make your work less in the end. So 5 times 6 is 30x, and then bracket 3x squared minus 1 to the 4. So do you see why taking the second derivative is a pain? It's because even though it wasn't in the first place, we do have the product rule now. So I'm going to need some space. And again, I'm going to do the textbooky version, meaning I'm not going to break it up into the green writing and taking the individual derivatives. So the derivative of the front, 30. That is not bad. Multiplied by the plain old back. Plus for product rule. Derivative of the back. This is where bad things happen, or lots of work happens. So drop the 4, keep writing, make it a 3, go inside, take the derivative of 3x squared minus 1, which is 6x, and then after all that's over, remember to multiply by the front. It's a lot of hard work. Then at the front, multiply your monomials. There isn't any. After the plus sign, multiply your monomials. There's actually quite a bit to do back here. So repeat. Plus, so this is 24 times 30. So 720 x squared, because of this, and then in a bracket behind 3x squared minus 1 to the exponent 3. Now, if you want to, you can do all your common factoring stuff. In fact, if it asked me for the third derivative, I would absolutely do that. But the question isn't actually asking for the third derivative. It's asking, again, to take the second derivative, and everywhere there's an x, plug in a -2. So I'm going to do that now before factoring, because it really doesn't matter what order you do it in, as long as you can follow BEDMAS. So again, we're plugging -2 in for all the x's. So tell me you're going to do that, and then do it. So it needs leveled brackets. So square bracket, round bracket for the -2 going in where the x is. Keep writing. Here's another x, -2, keep writing. There's another bracket, so I'm going to square bracket it off. -2 where there's an x, keep writing. Then I'm going to do some BEDMAS and then in a minute clean it up. So this is +4 times 3, which is 12, minus 1, which is 11 to the 4, plus 720 times +4, -2 squared. That's 4 times 3 is 12, minus 1 is 11 to the 3. So I'm going to let my calculator do the work here. So I'm going to do 11 to the not quite. 11 to the exponent 4 equals a giant number times the 30 out front, 439,230. 439,230 plus 11 to the 3 is that, times the 4 that's in front of it, times 720. Yikes. 3833 280. And while that's on my calculator, I am going to add on 439,230, that number, equals 4272, 4,272,510. So that is the answer to our question. Again, no real purpose other than to practice skills. Oops. Let's try that again so it's neat. There we go. All right, so higher order derivatives, meaning you can take derivatives from now to the end of time. There's the questions on page 106 of your textbook on calculus and vectors. I will be back to do, hopefully today, the 23rd of December, of the worst year yet. I am going to come back to do I'm going to call them co-videos from now on. I'm going to come back to do my co-video that requires graphing and how that does apply to graphing, because calculus and graphing do go hand in hand. So that is all for now. Let's see my time. Oh my gosh, so short this time. See you in a bit.